Good morning, everyone, and welcome to the fourth webinar of the Coffee Talk series, which is organized by the Early Career Chemical Engineers of section of the European Federation of Chemical Engineering. My name is Theodoros Papalas, and as the chair of the Early Career Chemical Engineers section, I'm very happy to have the chance to moderate this session, and I will do this together with Ulderico Caprio, who is also a board member of our section. A little bit about the Coffee Talks. This is an initiative that we have started in order to give the chance to the working parties of the EFCE to introduce themselves. And in this way, they can talk a bit about the activities and the events that the working party is doing, and also the fundamentals behind the research field that they are working on. Together, today we are collaborating with the Working Party of Process Intensification, and it will be a special coffee talk event because, except from the standard procedure that we are usually following, this will be later followed by a presentation on real case process intensification examples through the results of the European SIMPLI-DEMO project. Today with us, we have two members of the Working Party, and I would like a bit to introduce these two members. The first one is Professor Georgios Stefanidis, who is also the chair of the Working Party of Process Intensification. Professor Stefanidis holds a master's degree in chemical engineering from the National Technical University of Athens and a PhD degree in the same field from Ghent University. He has been PI or coordinated several research projects and also co-authored over 150 peer-reviewed papers in the broad field of chemical reaction engineering and process intensification, mostly focusing on alternative energy forms and transfer mechanisms. His research activity includes modeling design and development of intensified reactors and reactive separation processes for a broad range of applications, including, among others, biomass gasification, reforming of hydrocarbons and oxygenated fuels, CO2 utilization, polymerization, and reactive crystallization. And the other member that is here with us is Professor Tom van Gerwen, who is full professor at the Department of Chemical Engineering in KU Leuven in Belgium. His research fields are in the development of sono and photoreactors, as well as the use of modulated flow in chemical processes. Tom was the chairman of the EFCE Working Party of Process Intensification for 8 years, between 2016 and 2024. And he is currently chairman of the European Society of Sonar Chemistry, and he is also board member of the Europic, a knowledge exchange platform on process intensification with 18 chemical companies being member. Tom has coordinated several European projects, and of which the SIMPLI-DEMO project is the one that is currently running. So a bit on the agenda of today's coffee talk. Initially, we will have a presentation about the fundamentals and the activities of the Working Party. This will be followed by a Q&A session, so please, you can put your questions in the Q&A box. And then we will have the presentation on the SIMPLI-DEMO project. And with that, I would please like to pass the floor to Professor Georgios Stefanidis, who will do the first presentation. The floor is yours.
Yes, thanks, Theodoros. Does it work now? Screen?
Yeah, yes, everything's fine.
Okay, no, thanks again, Theodoros, for this nice introduction and for giving us this opportunity. What I would like to talk about today is PI as an evolution in chemical process design. I'll begin with some historical development and then move towards the physical principles that distinguish PI from conventional approaches. So PI actually has its roots in space research. During the 60s and the 70s, space-related research revealed how strongly gravity influences transport phenomena. Reduced gravity modifies buoyancy, film formation, and gravity was already identified as a governing parameter in hydrodynamics and mass transfer. And that insight later inspired Colin Ramshaw from the ICI group, who actually posed the inverse question. What if gravity is increased artificially? And the high G concept that he devised addressed that by applying centrifugal acceleration 100 to 1000 G to gas liquid systems. This photo here is a photo from a high G distillation unit. So high G, it was found that high G reduced film thickness, it enhanced interfacial renewal, and it increased dramatically mass transfer coefficient. So that was an early example of deliberate modification of a physical constraint that shifted mentality from accepting certain limitations to redesigning governing parameters. So the term process intensification appears for the first time in the 60s in the literature of metallurgy. At this stage, PI meant simply process improvement, improving yield, reducing processing time, increasing operational efficiency. There was no unified physical framework behind it, no concept of altering governing transport or thermodynamic constraints. So the term existed, but the paradigm did not yet exist back then. In 1983, in a meeting of ICME, Colin Ramshaw, as I mentioned before, introduces high G for the first time. He talks about exceedingly compact plant, an order of magnitude equipment reduction, and compactness was achieved by altering the transport regime, not by shrinking the geometry. Centrifugal acceleration replaced gravity as the governing hydrodynamic parameter. Interestingly, the first paper that was presented in that conference was on intensified gold ore leaching. The authors talked about solid liquid mass transfer intensification. So liquid mass transfer was the bottleneck of that process. So it is clear that early PI was already targeting dominant transport limitations and physics-driven redesign. In the 80s and the early 90s, PI was mainly a British discipline. The focus started being on centrifugal forces, as I mentioned before, and then it evolved towards compact heat exchangers and intensified mixing. In 1995, there's the first dedicated process intensification conference that was organized by PIN UK, the Process Intensification Network of UK. And in the late 90s, there are several international research centers that emerged in the States, in France, in Germany, in China, and several PI technologies were studied there. And in the late 90s, the involvement of the industry in the field of processification becomes more prominent. Companies like Eastman, Dow, DSM start validating the performance scalability, robustness of certain PI technologies, such as reactive distillation, rotating packed beds, microreactors, static mixers. And the validation is done beyond academia, beyond academic environment. In the early 2000s, and from that moment on, there is a clear shift from compact equipment to sustainability-driven redesign. There is the recognition that transport and energy efficiency are central to decarbonization. PI becomes institutionalized. There are more conferences, textbooks, journals, and research networks that work on process intensification. PI is integrated into EU research programs and strategic roadmaps. So there's what we observe is a clear transition from innovation concepts to a more structural engineering paradigm. If you scan the literature, there are several, more than 20, I would say, definitions and interpretations of PI, of process intensification. I've tried to classify them into different groups depending on the age that each definition appeared. So in the early 80s, as I said before, the focus is on compactness. This is the keyword, compact equipment, order of magnitude reduction. In the late 90s, people talk more about novel design approaches and innovative technologies. In the early 2000s, they talk about drastic improvements in processes. It is from, I would say, the middle of the first decade of the 2000s on that people start recognizing processification as a holistic approach to redesign processes and equipment within the broad field of chemical engineering. From all the available PI definitions, this is my personal favorite. It was published in the European Roadmap of Processification in 2007. It reads as a set of often radically innovative principles, a paradigm shift in process and equipment design, which can bring significant more than a factor 2 benefits in terms of process and chain efficiency, cutting expenses, quality, waste, and process safety, or to put it more simple, using much less to produce much more, less meaning investment, space, time, raw materials, energy, inventory. Much would mean drastic improvement, factors, orders of magnitude, ideally, of improvements. Of course, the exact quantified benefits vary depending on the authors that report these benefits and will work in the field of processification. This is another report that was published in 2006 by Center Novum, the Dutch Energy and Environmental Agency. They report energy savings in the range of 20 to 80%, capex and opex savings 20 to 80%, selectivity and yields increase up to 10 times, even more, and significant process safety increase as the reactor volume and inventory of chemicals decrease up to 1,000 times, and there's better control of reactions. Another interesting aspect that is not clear in the mind of many people, I would say, or several people in the field of chemical engineering, is the relation between PI and process systems engineering and how these two fields differentiate and become complementary. As we see in this figure, PSC, process systems engineering, operates primarily at plant site and enterprise scales, targeting optimization and integration of existing process units. PI, on the other hand, operates at molecular scale, particle scale, thin film scale, up to process scale, targeting modification of the dominant transport and reaction environments. So PI targets characteristic length and time scales, reducing diffusion paths, narrowing residence time distribution, enhancing interfacial renewal, increasing reaction rates, and it shifts focus from flow sheet optimization, which is the main goal of PSC, to phenomenon level redesign. So PI acts bottom up, as you see, and process systems engineering acts top down. This is a nice figure, I believe, that illustrates the distinction between the PSC and process intensification. What you see on the left is actually a medieval gold extraction process from the book De Re Metallica, which shows classical PSC thinking. You see grinding, crushing, and mixing that are integrated mechanically into a coordinated process system. This is what PSC does. PSC integrates steps. On the right hand, and by the way, the situation has not changed much today. But the important thing here is that you see the motionless mixer that represents a fundamentally different concept of mixing compared to a stirred tank. This is actually the essence, the epitome of process intensification. It introduces a new mechanism for the same function. So PI does not integrate existing units; it replaces them with new physical concepts. Now, in the early 2000s, PI was often described as a toolbox of technologies. It consisted of two main categories. Actually, the first one was, you see it in the upper part. It was the group of process intensifying equipment. such as novel reactors, intensive mixing devices, compact heat exchangers, or rotating packed beds. The second one in the lower part of the figure is the process intensifying methods, including hybrid separations, multifunctional reactors, alternative energy sources such as microwaves or ultrasound, and dynamic operation strategies. This classification was useful back then because it organized somehow the rapidly growing number of intensified technologies. But it's not sufficient for systematic process development, as it lacks a generic multi-scale design framework. That realization leads to the need for a more fundamental understanding of processification and brings me to a well-known paper and Andrei Stankiewicz, The Fundamentals of Processification, published in ICR in 2009, and the contents of that paper were further updated and elaborated on in a book that all three of us, Andrei, Tom, and myself, wrote in 2009 with the same book, has the same title, The Fundamentals of Processification. It was published by Wiley that year, and explains our view on the fundamentals of processification, and I would like to mention some elements of this of our approach. So to move beyond isolated technologies, we must first define the ultimate goal of an intensified process. An ideal intensified system is one in which reactions proceed at maximum achievable efficiency. All modes under transport and synergy effects between steps are fully exploited. So from these definitions arise four generic principles. The four principles of processification provide a multi-scale, holistic foundation for processification. And they shift the focus from equipment categories to fundamental physical objectives. And I'll start with the first principles. The first principle, maximizing the effectiveness of intra and intermolecular events. Classically, the reaction rate is described by the Arrhenius equation. We increase rate either by increasing temperature through heating or by decreasing activation energy using catalyst. But there's a third parameter, which is also important, the pre-exponential factor that reflects the frequency and effectiveness of molecular collisions. If we want to intensify reaction fundamentally, we must ask whether collision effectiveness itself can be engineered. The answer is yes, at least in certain environments. This is a famous work by Zar. It's a science paper of 1998. The authors apply a laser to a molecular bin of methane in order to stretch the CH bonds, in order to make the hydrogen atoms more visible to chlorine, to increase the frequency of effective hydrogen chloride formation events, and indeed the reaction rate increases by more than 2 orders of magnitude. So chemical reactions occur through molecular collisions, yet the vast majority of these collisions are ineffective. In conventional reactors, we energize molecules through conductive heating. This is non-selective. All molecules are heated, not just the reacting ones. So instead of having controlled collisions like I would say snooker player deliberately directing its impact, we create a pinball machine with random motion, random impacts, and broad distribution of molecular energy. This lack of molecular level control is the core limitation of current reactor design. So conductive heating also creates temperature gradients inside the reactor. As a result, molecules do not all possess the same energy. Some have insufficient energy to react. Some have excessive energy, and some have enough energy to initiate undesired side reactions. In parallel reaction systems, this broad energy distribution directly reduces selectivity and increases waste. So ideally, we would like to supply all molecules with a narrowly distributed amount of energy, just sufficient to cross the desired transition state and no more than that. This is the objective of principle 1, creating a reaction environment where intra and intermolecular events are controlled rather than left to statistical chance. The second principle follows naturally from the first one. If we want to have effective molecular events, we must also ensure that all molecules experience the same history inside the reactor. In an ideal intensified process, every molecule should undergo identical residence time, identical thermal exposure, identical mixing conditions, because uniform processing minimizes variability and waste. But in conventional reactors, molecules do not experience the same conditions. In stir-tank reactors, for example, residence time distribution is broad. Some molecules live too early, others remain too long. And on top of that, temperature gradients further broaden the distribution of molecular events, of molecular energy levels, I'm sorry. Even in plug flow systems, uniformity is defined only at macroscopic level. At the molecular level, motion remains random. So in fact, true molecular uniformity would require narrow energy distributions and minimal spatial thermal gradients. And in this regard, application of external fields can play an important role here. So the goal of the second principle is to reduce residence time variance, eliminate dead zones by passing suppressed hotspots, and minimize micromixing heterogeneity. Regarding the third principle, uniform process conditions require efficient transport. Efficient transport in turn depends on strong driving forces and high interfacial area, unless external fields are applied. So processification here fundamentally means increasing the effectiveness of the driving forces, heat, mass, and momentum transfer, and maximizing the interfacial area over which these forces act. Since most chemical processes are transport limited, increasing transfer area per unit volume is one of the most powerful levers that we actually have. So the surface volume ratio scales inversely with the characteristic diameter, as you know, the A over V factor equals 4 over D, which means that reducing the characteristic dimension by 1 order of magnitude increases the available transfer area per volume also by 1 order of magnitude. So when we move from meter scale equipment to millimeter or micrometer scale, we increase interfacial density dramatically and therefore enhance heat and mass transfer rates. And by the way, nature has already optimized mass transfer by minimizing the characteristic length scales, the existence of capillary networks which enable the exchange of oxygen, CO2, and nutrients demonstrates that ultra high interfacial densities in the order of 400,000 meters square per cubic meter are both functional and sustainable. So the question for chemical engineering is how to translate this principle into scalable reactor design. Traditionally, chemical processes are divided into separate unit operations: reaction, separation, heat exchange. PI challenges this separation by combining partial processes into multifunctional units. We can create synergistic effects. For example, coupling reaction separation shifts equilibrium, combining mixing and energy input enhances transfer rates. This is a simple example on reaction. The sequential methylation leads to a mixture of 1- MMA and DMA are the two desired ones. By adding a selective membrane layer around the catalyst, the desired products can diffuse out preferentially, and this shifts the local reaction environment and significantly increases selectivity. So this improvement is not only due to better catalyst, but due to the coupling of integration with the coupling of reaction and separation. So, so far I have discussed fundamental principles of processification. The next question is how these principles are realized in practice. In general, intensification strategies can be organized into 4 domains: spatial, thermodynamic, functional, and temporal. I'll start with the first domain, the spatial domain, where processification means replacing randomness with structure. as discussed, randomness in catalyst beds, reactors, and fluid distribution leads to maldistribution, poor predictability, and safety risks. Introducing a reproducible structure improves control, modeling reliability, and scale-up. These structures exist at multiple scales. At the molecular level, we have cages and imprinted systems that control molecular orientation and selectivity. At the mesoscale, you see monoliths, foams, corrugated packings that enhance heat and mass transfer, while reducing pressure drop. At the macro scale, in the lower part of the slide, you see fractal distributors and structured internals that ensure good flow distribution. So the common idea here is simple: to design the spatial organization deliberately in order to improve transfer rate, selectivity, energy efficiency, and safety. An industrial example from DSM in traditional stir tank reactors, mixing and heat removal occur in large vessels. Heat is removed through a jacket or internal coils. Temperature gradients may develop that especially in fast exothermic reactions. In the microreactor technology, the same chemistry is carried out in thousands of microchannels. And as I said before, because the characteristic dimension is drastically reduced, the specific heat transfer area increases dramatically, and heat removal becomes extremely efficient. As a result, the reactor inventory is reduced from 10 cubic meters to only 3 liters, while maintaining the same capacity, 1,500 kilograms per hour. And also the improved temperature control leads to 20% better selectivity. That in turn leads to better material yield. After structuring space, the next major level for processification is energy. The chemical industry is highly energy intensive. Most of it and much of this energy is supplied in a non-selective way, typically through steam boilers and external heating surfaces. In the thermodynamic domain, by intensification, we mean changing how the energy is delivered to the system. Instead of indirect surface-based heat transfer, we can use alternative energy forms such as electric fields, electromagnetic radiation, plasma, acoustic energy, to interact more directly with the molecules. So in this regard, the energy becomes not just a utility, but a tool to influence the reaction rates, transfer phenomena, and thereby selectivity. So different energy forms you see on this slide. Different energy forms interact with matter in fundamentally different ways. Electromagnetic radiation from microwaves to lasers can induce molecular rotations. Vibration and electronic excitation. This enables volumetric and selective heating rather than surface heating. Acoustic fields generate cavitation bubbles. Their collapse creates localized extreme conditions, high temperature and pressure, which can intensify mixing and drive chemical reactions. Plasma fields generate reactive species such as radicals, ions, and other energetic species that allow activation of very stable molecules, for example, methane or CO2. Supersonic flows and shock waves convert kinetic energy into rapid compression and extreme local conditions that enhance phase contact and reaction rates. And another industrial example in the domain of energy, in the thermodynamic domain. This example illustrates processification through use of high gravity fields. It was a Dow chemical process. In the conventional process, hypochlorous acid is produced in adsorption stripping columns. The key challenge is that hypochlorous acid is unstable and must be removed from the reaction environment as quickly as possible to prevent the composition and side reactions. In an intensified version, reactive stripping is carried out in a high gravity rotating park bed. By rotating at high G, at high speed, centrifugal forces up to 500 times interfacial area and mass transfer rates. And as a result, you see the benefits here. Because of the fact that the product is removed immediately from the reaction zone. The consequences is that the equipment size is decreased by a factor of 100. Product yield is improved by 15%. There's 50% reduction in the stripping gas, 1/3 reduction in waste and chlorinated byproducts, and all that while maintaining the same processing capacity. The third domain of processification is synergy, the functional domain. Here, intensification is achieved by combining functions that are traditionally separated, reaction and separation, mixing and heat transfer, adsorption and catalysis. The objective is to create a system whose performance is better units. And these are examples that illustrate functional integration in processification, a membrane reactor, chromatographic reactor, a static mixer heat exchanger, a reactive distillation that integrates reaction separation, single column monolithic stirrer reactor that combines catalysis and mixing. The common benefit is, again, improved selectivity, better conversion, reduced equipment count, and a lower energy consumption. And of course, more compact and more efficient process. An industrial example comes from the Eastman Chemical Company. In the conventional methyl acetate process, 18 separate units are needed in order to produce methyl acetate due to azeotrope separation issues. By integrating reaction separation in a multifunctional column, combining reactive and extractive distillation, the entire process is reduced to just 3 units, and the result is 85% energy consumption reduction and about 80% lower investment. And the fourth domain is time. Here, the key manipulated variable is the temporal operation. We introduce control periodicity or extreme shortening of contact times to manipulate some time scales. Instead of steady state operation, we deliberately use oscillations, flow reversal, cyclic operation, millisecond contact time reactors to enhance transport, heat management, and eventually selectivity in yield. These are examples of some CPI technologies, oscillatory flow reactors that generate vortices through periodic motion, enhancing mixing while maintaining plug flow behavior, reverse flow reactors that periodically switch flow direction to generate heat and enable autothermal operation, short contact time reactors that use millisecond residence times to control selectivity, periodic feeding of CSTRs to introduce controlled concentration oscillations and enhance selectivity. And again, an industrial example from the James Robinson Company, a specialty chemicals manufacturing company. A 27-meter batch reactor was replaced by a compact oscillatory flow reactor. And the result was 20 times reduction in footprint and process time with lower cost energy use and waste. And that concludes my presentation on the fundamentals of PI. If I can put it in one sentence, PI is essentially the deliberate control of phenomena across all spatial and temporal scales. Very briefly, on 3-4 slides on the working part on processification. It's almost 20 years old. It started actually from an initiative of the of NPT, the Dutch member society of EFCE, to establish a new working party in the area of processification. In July 2005, the General Assembly of EFCE approves the establishment of the working party on processification. And in May 2006, about a year later, there is the inaugural meeting of the PI Working Party in the premise of DESA9 Frankfurt. Our aim is to advance PI approaches and technologies both in academia and industry, promoting education, dissemination, and collaborative research. And through European international partnerships, we aim to accelerate innovation and the practical implementation of intensified processes. At the moment, we have 32 members in our working party, 17 academic delegates, 9 industrial delegates, 3 elected members, and 3 guest members. And our activities our main activities at least is 1 or 2 business meetings a year. We organize or co-organize workshops and webinars. For example, we do at least one spotlight talk webinar every year on various PI subjects, often in collaboration with other EFCE entities like the CRE Working Party and the MFF Working Party. Now there's a new section in the EFCE that is actually under organization, a section on artificial intelligence, and we're going to co-organize joint webinar on the application of AI to or relation of AI and process intensification probably in April. We organize dedicated PI sessions in international conferences like ECCE, KISA, and NISCRE. We deliver 2 PI awards biennially. The PI Excellence Award for the best PhD dissertation in the field of processification and the PI Award for Industrial Innovation. And we have established international collaborations with relevant societies in America and in Asia, like the American Institute of Chemical Engineers and the Chemical Industry and Engineering Society of China, to organize joint initiatives, for example, the biennial own conference series in Europe on processification. It's called EPIC, European Processification Conference. It is held every 2 years. Recently in Athens, we had EPIC 9. That was last June, and the next one, EPIC 10, will be on September 26 to 29, 2027 in Bologna, Italy. And with that, I would like to conclude my presentation. Sorry for taking longer than expected. Thank you very much for your attention. If there are any questions, I'll be happy to address them.
Thank you very much, Professor Stefanidis, for the very thorough presentation on process intensification. For the audience, please, if you have questions, you can put them down in the Q&A session, and we will ask them later. But for now, we as early career chemical engineers, we do have some questions that we would like to ask you, and that we have prepared. So the first question is, what are the core criteria for deciding whether a process is a good candidate for process intensification?
Yeah. Is it me? Is it Tom?
It can be both, but please, if you would like to start.
Yeah, when is a technology a good candidate for processification? I would say that there must be certain limitations that should be addressed. For example, when transport limitations dominate, heat or mass transfer limitations, when selectivity is sensitive to gradients, when equilibrium shifts, when equilibrium limits conversion in yield, for example. When inventory and safety are concerns, when upscaling is problematic. When you have such problems, such limitations, then you have to think of PI approaches in order to address them. There must be a problem that should be one of these problems that should be addressed by some of the PI technologies that I presented.
Okay.
So when a process is limited by scale, temporal or spatial, then PI can improve the process often dramatically.
Okay, thank you very much for the answer. If we can go to the second question. What are the most common mistakes that companies make when trying to implement process intensification for the first time?
For the first time? Well, first of all, let me tell you that a problem that I see when I talk to industrialists, and this is pretty often, is that they are unaware of benefits and potential of PI technologies, but also the limitations and the downsides. They are not well educated in that field. They miss information. There is a fair amount of ignorance about process intensification and what can be achieved by process intensification, and this certainly slows down, let's say, broad adoption of PI technologies in chemical industry. This is what I see as the main challenge of having more PI implemented in chemical industry. Now, beyond that point, when they try to implement PI for the first time, yeah, I mean, a very common problem is that they put the cart before the horse instead of them looking for the bottlenecks in their processes that can be addressed by process intensification. They think the other way around. They see a technology, or they know the technology. It can be microreactor, it can be microwave, plasma, whatever. They say, okay, what can this technology do for us? But this is not the right way of thinking. They have to first think about the limitations of their own processes. Very frequently, to give you a concrete example, we see processes, liquid phase process in chemical industry, running for days. They let the reactor work for several hours overnight. And when you ask them, why so long? Why would the chemistry take so long to complete? It doesn't make sense. 24 hours, no chemistry needs so much time to reach a desirable yield, a desirable conversion level. They don't know. Of course, there are mixing limitations, there are mass transfer limitations, there are heat transfer limitations, but they don't think in these terms. So they don't think after that what PI can do in order to address their problem. I think this is the most important problem. Also, there's certain ignorance in operability and control. Integration of a new PI technology into an existing workflow, and even the PI technology alone requires a new control strategy, a new it requires a new thinking, a new mode of operational thinking, and they are not aware of that. They just see PI as, okay, we're going to add one new piece of equipment into our plant, but it's not exactly like that. The integration changes a lot. Changes operability, changes flexibility, changes the operating window, changes controllability, changes everything, and they don't realize that immediately. Several people still see PI as addition of one new piece of equipment, sexy, modern, into their plant.
Thank you very much. Thank you very much for the answer. I can go on with the next question. That is actually about education and how well do current chemical engineering curricula prepare students for working in process intensification, and what topics do you think should be better integrated into undergraduate education?
Yeah, well, as chemical engineers, we're typically, at least in good universities, well educated in some pillar subjects like thermodynamics, transport phenomena, chemical reaction engineering, but PI goes beyond that. It requires good thinking, deep thinking in terms of multi-physics thinking, and often these new physics that are brought in by PI technology are quite complex. If we're talking about, for example, ultrasound or microwaves, electromagnetic fields, these are relatively, as chemical engineers, we're not well educated in this type of physics. PI often requires also dynamic operation, process control under unsteady state conditions, system level thinking, advanced process control. All these aspects I would say in most chemical engineering curricula are superficially tackled or studied. We need better education in these subjects in order to understand PI better and advance PI and promote its deployment in chemical industry. Sustainability and life cycle thinking is also another, because it has become a design constraint for processification. So sustainability and life cycle thinking is another aspect that requires, I would say, at least one dedicated course in each chemical engineering curriculum. That would also help understanding of processification.
Thank you. And talking about sustainability, it's also involved in our next question, that is about how sustainability metrics influence the decision on when designing intensified processes.
Yeah, sustainability is a core design constraint and factor that influences PI a lot. Metrics such as energy intensity, CO2 footprint, the E factor, often justify use of PI economically, financially. So they support, these factors support the use of processification in order to achieve certain quantitative metrics on energy intensity, CO2 footprint, and E factor. So smaller equipment, for example, embodies lower carbon contents. While those in-situ separation reduces energy demand. So contact times reduce waste. All these PI approaches and PI technologies help achieve certain sustainability metrics.
Thank you. And our last question is about the future of PI as we live in a continuously evolving scientific landscape. And what do you think the next big change will be in process intensification?
Yeah, the next big change. It's certainly not going to be a certain technology or drastic improvement of certain technology or a new technology. I think this field is more or less mature in terms of development of new technologies. What I see as new trends is the adoption of electrified reactors that work on renewable electricity, for example, microwaves, ultrasound, plasma reactors, real-time adaptive control, AI-driven process control, and modular distributed manufacturing. I would say these four aspects constitute the new trends in process intensification.
Thank you. And we are finished with our questions. Now the floor is open for questions in the Q&A. And I see we already have a question.
If Tom wants to add something, I mean, I don't want to speak only myself. Please, I don't know, Tom, if you want to step in anytime.
You've said everything. You're just perfect answers.
And we have a question from the Q&A, and it says, some student feels that process intensification is taught mostly through examples and case study with fewer systematic calculation than reactor engineering. In your view, does PI have unified theoretical framework and set of teachable calculation method? How do you see the field developing in the future in the terms of theory, model, and standard design tools?
No, I wouldn't say that there is a unified theoretical calculation framework. But as I said before, there are certain aspects, for example, multi-physics education and thinking, dynamic operation, system level design, thinking, sustainability factors. So if one to evaluate a PI technology and optimize a PI technology or a PI process has to be educated in these terms, has to understand, for example, the theory of electromagnetic radiation, its transportation and its dissipation, or plasma physics. There's, of course, deep theory behind all these subjects, transport phenomena at microscale, how transport phenomena change under high G in a high G environment. So the first step is for interested students and professionals to get educated in these fields, understand the theory in these subdomains, and then they will be able to advance calculations and optimization of PI technologies.
Thank you.
Yeah, this is the approach.
Thank you for the answer. I don't see any further question in the Q&A, so we will leave a few seconds if someone wants to ask. Just been answered. Okay, so if there are no further questions, we'll move to the second part of this presentation that is about the SIMPLI-DEMO, and I will leave the floor to Professor Tom van Gerwen from KU Leuven.
All right, thank you very much. I'll share my screen.
Yes.
All right, so let me see how it works. So you should see at this moment the full scale presentation.
Yes.
Okay, good. So thank you very much for being here. I see that a couple of colleagues from the SIMPLI-DEMO project are here as well. What I'd like to do is to introduce you a little bit to the SIMPLI-DEMO project, which is a currently running European project. We're in the last phase of the project. It's a 4 years project, and we're more or less 3.5 years far. So most of the results have been obtained, and of course there's some final demonstration phase that is now running. SIMPLI-DEMO project is dealing with electrical and electromechanical activation of liquid-based processes in the chemical industry. And I'd like to talk a little bit. So I'll see if I hope I can do it within the provided time. First, I'd like to introduce a little bit of the project context, talk a bit about the PI technologies involved, some results on the integrated processes, and I also want to talk about some economic and environmental considerations, and in the end I'll conclude. So what's the SIMPLI-DEMO project about? Long title of the SIMPLI-DEMO is the demonstration of sonication and microwave processing of essential chemicals. So you see immediately that sonication, ultrasound on the one hand, and microwaves on the other hand, are two important alternative energy forms. And as Yorgos spoke in his previous presentation, these are two energy forms that we consider to be useful in the process intensification domain. The perspective that we have taken in this process or in this project is that we believe that these alternative energy forms, ultrasound and microwaves, can act as enablers for the transition of batch to continuous processing. And we particularly see that for two types of difficult processes that are difficult to transfer from batch to continuous, which are on the one hand viscous phase containing streams, and on the other hand solids containing streams. So these are two processes where if you look into industry, into literature, it's not straightforward to find examples where these processes have been converted into a continuous flow system. And we think that this ultrasound and microwaves can help doing that transition. So as I said, we're focusing in SIMPLI-DEMO on two types of specialty processes. On the one hand, highly viscous streams, and there we're typically using reactive extrusion as the continuous flow technology. We have two end users involved there, Coatex, which is now part of Arkema, and we have also Mega Resins, a company involved. The end use cases are dealing with polyurethane production, both isocyanate based and non-isocyanate based, and also polyether synthesis. The other type of chemical process is the one involving suspensions, and there we're looking at reactive crystallization in an oscillatory baffle flow reactor, a COBR, as the continuous technology of choice. And again, here we have two end users. We have Arkema, who's interested in zeolite synthesis, and we have GE Healthcare, General Electric Healthcare, who's interested in API synthesis, advanced or pharmaceutical, active pharmaceutical ingredients. The idea of the project, or at least at the beginning and still is that we were supposed to move from TRL5, which means that the technology at the beginning of the project was validated in a relevant environment, to a TRL level of 7, which means that we have to demonstrate an industrial system prototype. And I will not touch upon that too much in this presentation, but it means that we have process control, process automation available, present on the different demonstrators, which allows us to work with these demonstrators for longer periods of time than what we would do in the lab. And so the overall goal is that we have an uninterrupted production, several days to weeks. We will see if we really can show that. We will certainly not show that for all the end use cases, but maybe for some of them. But in any case, what we already can show now is that we do have annual production rates. If you translate the production rate to an annual rate of 10 to 100 tons a year, which is a decent production for a pilot scale installation. Just a short word on the consortium. Obviously, as any European project, we're consisting of knowledge institutes, Leuven, Athens, Dortmund, Heriot-Watt in the UK, and Fraunhofer Institute of Chemical Technology in Germany are involved. And then we have companies. We have 4 end users, as I mentioned, Arkema, GE Healthcare, Coatex, and Mega Resins. Then we have 2 technology suppliers on the ultrasound and microwave side, Mügge for the microwaves, Weber Ultrasonics for the ultrasound, and so that there's also someone from Weber present here in the meeting. And then we have Leicon, who is involved with process automation, works very much in combination with Technical University of Dortmund, who's doing the process control. And then we have also Aristeng, who's doing the process design calculations and also the LCA calculations. The project approach was the following. SIMPLI-DEMO project was actually a project that followed on a previous European project, which was the SIMPLI-FI project. And in the SIMPLI-FI project, we already had 2 use cases relevant to Arkema and Coatex, meaning that we were...
verspätet jetzt, oder? Nee? Weil jetzt erst über SIMPLI-DEMO redet?
There's somebody's microphone on, so please turn it off. Thank you. In the SIMPLI-FI project, we were looking at one particular zeolite. We were also looking at one particular polyurethane. And in the SIMPLI-DEMO project, we're actually using that knowledge, that expertise built up with quite a lot of partners being involved in SIMPLI-DEMO and in SIMPLI-FI to further develop that to a higher TRL level. That's one thing that we've done in SIMPLI-DEMO. Another parallel route is that we also worked on other types of components, other types of zeolites, other types of APIs, other types of urethanes. Again, as I said, isocyanate-based, non-isocyanate-based, also polyethers, to make this transition from a low TRL to a higher TRL level at a much quicker pace. because of the fact that we could rely on the expertise from the previous Simplify project, but also of the running SIMPLI-DEMO project. So basically, where are we at this moment in the project? We're approaching the project end, which means that we've basically done the parametric validation of the different concepts. We've developed, as I said, further developed the two use cases that we also had in the previous project, and we've complemented that with other components that we've investigated. And we're now in the demonstration phase, basically at TRL 7 of the different technologies, the combined technologies, the integrated technologies, including process control and process automation. So which are the technologies involved? Basically, there's 4 big PI technologies. The first 2 are the ones that I already mentioned in terms of continuous flow operation. On the one hand, we have the oscillatory baffle flow reactors, which we are using. This is a kind of a tubular reactor where there's baffles inserted in the tube. And then if you have a pulsed flow, you ensure that you have constant turbulence, even at low net flow rates. So this is an interesting feature, because in the case that you have solids present or solids being formed during crystallization, often a big problem in tubular reactors is sedimentation and clogging, and you try to avoid that by having this turbulent flow, and again, even at low net flow rates, which still allows you to have a reasonable residence time. On the other hand, we're also looking at the reactive extrusion technology, which is a very common technology for high viscosity materials. And there we're applying reactive extruders, REX technology, for the different types of polyurethanes and polyethers that we're producing. And as I said before, we're combining this with ultrasound and microwaves as non-contact energy forms. Ultrasound mostly for improved mixing, improved mass transfer within these tubular reactors. Microwave mostly for improved heat transfer in these tubular reactors. And so if we then look at how we've done that, how we've demonstrated those or integrated those processes, I'll give you a very short overview of some of the results. Of course, I cannot go over all the results. There's also some results that we're not able to share, but I want you just to show you the overall picture here. So the way that we went about this is we first started with this continuous flow system, and in this case, I'm showing you a picture of a reactive extruder, which we optimized for this particular set of chemistries, again, polyurethanes, polyethers. And then only in a later phase, we started to integrate ultrasound and the microwave into these reactive extruders. And of course, in parallel with our first part of the investigation, where we looked at the reactive extruders, we also looked at individual the individual energy forms, ultrasound and microwaves, but the combination, the integration of ultrasound and microwave with the reactive extruder only came later into the project. So the overall view was that we would enhance the application or the operation of the extruder with the use of ultrasound and microwave. And interestingly enough, we were going to do that in a modular fashion, which means that we have designed ultrasound and microwave antennas in such a way that we can basically apply them to a certain module within the extruder, and we can move that module around, placing it where we want, a bit more upstream or a bit more downstream in the system. And this allows us also to be flexible in terms of the different chemistries that we're applying. Now, a first thing that we needed to do was to apply the chemistry to the reactive extruder that took us some time to optimize that. As you can see here, in a first instance, we were not able to replicate the same product properties of certain products in the extruder compared to the properties in the batch operation. But then by further optimizing the chemistry, also looking at where exactly do we need the extruder. In some cases, or in this particular case, we said, let's look at the first two steps of the polymerization process and use there the reactive extruder. The third step is something that we will do then in batch. And this allowed us to get much better product properties in the end. So this is an adaptation, and this is something I think we always need to do, an adaptation of the chemistry, which usually is optimized for batch. We need to optimize that for the flow technology. And then we further went with, a lot of things, the chemistry optimization was done at the laboratory scale. Then we moved to the pilot scale, the continuous scale, in a first pilot, and then in a second pilot or production scale. As you can see, the throughputs went from 0.5 up to 10 kilograms per hour to up to even 60 kilograms per hour. If you calculate that to an annual throughput, you're into the hundreds of tons per year. And as you can see, the fact that we were playing or we were working with different chemistries allowed us also to move ahead with the chemistry that we knew well from a previous project, where already now or already some time we are at the TRL7. The others are a bit behind, but we hope we can move them up to higher TRL levels in the last few months of this project. This is mostly the reactive extruder for this synthesis of these urethanes. We also looked at the integration of microwaves, and this is work of actually the group of Yorgos Stefanidis, the speaker of the previous presentation, where we looked at temperature cycling, and using microwaves, we are not bound by the inertia of typical steam heating or other types of conventional heating, and this allows us to go to a very quick turning on and off of the heating source, which allows us to go to temperature cycling. And you see here different profiles of temperature cycling, moving up to spikes of 230, 220 degrees. What you see here in the different colors is the average temperature between minimum and maximum time-weighted averages. And then if you look at the results in terms of the molecular weight that you produce, you see that these average temperatures actually are, but in a pulsed, in a microwave cycled or temperature cycled fashion, we're able to achieve much higher molecular weights compared to the conventional heating. So for example, here, conventional heating at 140 degrees. If you compare that with an average temperature profile of 134 to 148 degrees, you see that with the microwaves, you can obtain much higher values, much higher molecular weights of the final product. The technology suppliers also worked on the upscaling of their technologies of the microwaves and ultrasounds with reactive extruder. I'm just showing you some results of the microwaves, not of the ultrasound. But this is equally important. We need to adapt the microwave and ultrasound antennas so that they can be integrated effectively in the reactive extruder or later on in the oscillatory baffle flow reactor. Coming to that oscillatory baffle flow reactor, so this was used for another set of applications, more the suspensions type of processes, where we had suspensions of zeolites or APIs, depending on the end use case. And again, we took the same procedure. We started with the COBR, the oscillatory baffle flow reactor. We optimized the chemistry for that continuous flow system, At the same time, we investigated on the lab scale the effect of ultrasound and microwaves, and then later on in the project, we integrated the ultrasound and the microwaves into the OBR system. In the previous, with the reactive extruders, I focused more on the microwaves. With the COBR, I will focus more on the ultrasound, just to give you a flavor of the different combinations that we've investigated. So again, an overview of what we try to achieve with this combination. At the heart of the process, there's the COBR reactor, where we're performing the crystallization either of the zeolite or of the API. It means that we have different raw materials, different feed streams. You need to mix them. We need to bring them into the COBR, and then we're looking at the application of ultrasound and microwaves in this COBR reactor. And then afterwards, of course, there's the whole set of separation and downstream purification of the different products. So again, similar to what I showed with the reactive extruders, we needed to optimize the chemistry towards the continuous flow system, towards the COBR. We had to adjust certain parameters, temperature, pressure, flow rate, to get a certain quality which was according to specifications. And as you can see, this was nicely done. You see here nicely produced, very homogeneous or uniform crystals of different types of zeolites that we were able to produce within the COBR. And then later on, we started to apply or combine the COBR with ultrasound and microwaves. I'll focus now more on the ultrasound. There's different ways that you can use the ultrasound. You can use it early on in the COBR for nucleation, but we also investigated the use of ultrasound towards the end of the COBR more for deagglomeration. And this is something that we've also investigated. Obviously, I'm showing here the best results, but you can imagine that in such a project you have also less good results. I'm not going to show them here, but I mean it's a continuous study of trying to find the best operational variables to find where exactly these PI technologies can work, and it relates a little bit to what Jorgos said before. With PI, we're trying to open up new windows of operation, and it's often really finding the niche window where this PI technology operates best and where it really works better than the conventional technology. I just want to show you here with the ultrasound probe, we tested the stability of the ultrasound frequency in the system, proved to be very stable. And then if we looked at the capability of the ultrasound to deagglomerate the particles, we see that moving from point 2, which is before the ultrasound probe, towards point 3, which is after the ultrasound probe, you see a reduction in particle size or in agglomerate size. And you also see it here on the pictures, a clear difference between the coarser agglomerates before the ultrasound and the more finer deagglomerated particles after the ultrasound probe. At the same time, we're also looking at the on the lab scale to look at the optimal integration of ultrasound with different types of reactors. As you can see here, we are looking at batch operations with different types of ultrasound plate transducers, horn transducers. We're also looking at the COBR. We're looking at tubular reactors. What it's clearly shown is that when you try to optimize the calorimetric energy input for a certain effect, in this case particle size reduction, it's clear that setups have their own energy efficiency, and there is a lot of optimization to be done between different types of irradiation sources. In this case, again, plate type of ultrasound irradiation source or horn type of irradiation source, and so forth. And again, similar to what I showed in the reactive extruders, also the technology suppliers worked very hard and in collaboration with the end users to get the ultrasound probes and microwave probes into the COBR. And as you can see, it may be difficult to see, but at the bends of the COBR, we're introducing the ultrasound probes, and it is also something to be looking at. You have these rod transducers here. Well, the rod obviously has to go into the oscillatory baffle flow reactor, which means that it has to be smaller than the opening of the baffles themselves. So this is also a design constraint that needed to be taken into account. And then finally, what we also did is we looked at economic and environmental considerations. As I said before, this was mainly the task of our project partner Aristeng, which collaborated very much with the end users because they have, of course, a good view on energy, materials, costs, operational costs, capital costs, and so forth. The basic methodology was that, first of all, we tried to come up with good qualitative mass and energy, or high quality is what I meant, mass and energy balances, which then allows us to move to process economics with using empirical equations, using the research data from the project, also using vendor quotes and using expertise from the end users. This was all done in AspenTech software. We're using software to further optimize these mass and energy balances and optimize the process economics. And then often combining with Excel, we performed life cycle assessment and techno-economic analysis. All this led us to the possibility to compare CAPEX, OPEX, and also greenhouse gas emissions between a comparison between the conventional system and the intensified process. And this gives types of results like this. I won't go into detail, but what you can see is that we're comparing batch operation with continuous operation. We're looking at CAPEX, we're looking at OPEX, we're looking at greenhouse gas emissions, and in some cases we see improvements of the intensified technology compared to the conventional technology. Finally, I'd like to conclude two concluding slides here. On a qualitative perspective, we can say that these PI technologies allow us to handle higher viscosities, higher viscosity streams, high solids loading streams. This is possible to be handled, which means that you often have to, or you can allow less dilution of the reactants, which means that you reduce your solvent volume. And this is, of course, beneficial also from a material point of view or a material cost point of view. Secondly, because of those smaller process volumes, it's often easier to integrate heat and to avoid heat losses. Thirdly, because of the fact that we're using pulsed operation, both reactive extruder and oscillatory baffle flow reactors is using pulsed fluid pumping. We're combining that with ultrasound and microwaves. Those are all electrified technologies. So we can, these are processes that are suited for electrification, and they open the possibility of using renewable energy, which at this moment we didn't focus on, but this is a clear driver for reducing the energy costs. And then in some cases, we also saw that going from batch to continuous, we are able to recycle certain diluents or solvents, again, reducing materials or increasing materials efficiency, reducing waste generation, reducing materials feed requirements. So the basic two, or the two basic improvements that we can see from this transformation from the conventional process to the intensified process is that we can replace heat by renewable energy, and we electrify the process, and we are able to reduce the amount of mass handled because of the smaller volumes. And this leads to changes in CAPEX and OPEX. In terms of CAPEX, it's clear, it's a mixed story. We have to be clear about that. We see that in many of the four cases, in 3 of the 4 cases, we saw an increase in CapEx because of the new technologies, rotating internals, pulsing internals, powerful motors, and so forth needed. In some cases, we saw also a decrease in CapEx, and that was mostly due to the fact that the conventional process had a lot of the individual unit operations or units needed. As regards to OpEx, often you don't see that significant changes in OpEx. It stays more or less the same. But again, because of the fact that you can go to an electricity-based activation, electrification type of technology, the assumption is there that we will be able to invest or to use renewable energy supply. And that will allow us, the more that renewable energies come on the market, and we already see, if you look at those renewable energies, that these prices are dwindling, this will lead to an associated OpEx decrease for those electrified technologies. This is what I wanted to tell you. And so thank you again for having me here, and I'm ready for questions.
Thank you. Thank you, Professor Van Gerwen, for this nice presentation. It's always nice to see the application of process intensification. So for the audience, if you have any question, please ask it in the Q&A. I will be reading it. To start, I have one question, Professor. It is about the usage of computational tools in this project, because in the second part of your presentation, you use Aspen. So you have showed you the usage of Aspen and Excel for the calculation for the LCA, but also in the previous part, I've seen some CFD-like simulation, I guess, for mixing and for flow efficiency. So I was wondering, how does it support the transition from small scale to bigger scale in this? So how the Higidal tool support this transition from small scale to bigger scale in this project?
Yeah, well, I think, it's clear that on the level of, let's say, the lab installations, we support our designs often with CFD calculations, computational fluid dynamics. This is still feasible because you're looking at small volumes. Calculation time is not that extensive. Obviously, that becomes more complicated when you go to a complete, fully integrated installation on the pilot scale. There, I would say we are using there was no CFD modeling applied on those large scale installations. A second application of the CFD was definitely to design the ultrasound and microwave antennas. We have the companies on board, Weber, Ultrasonics, and Mügge. These companies, often in collaboration with the universities, applied CFD modeling to investigate what would be the best design for that particular antenna to irradiate a certain volume within the continuous flow system. And then, so this is CFD modeling. The Aspen flow or the Aspen modeling, that's a process modeling or flow sheet modeling software, which basically allows us to build a complete process design. I didn't go too much in detail, but what is also part of the project is the end users are, as much as possible, also including upstream and downstream operations, filtration, mixing of the reactants upfront. And these are things that, in the end, if you want to do a good techno-economic calculation, you need to also include those in the calculations. And this is then done, for example, with Aspen.
Thank you. Thank you for the answer, Professor Van Gerwen.
Ulderico, can I also ask a question?
Sure. Go ahead.
Okay. Thank you also from my side. I agree with Ulderico that seeing real case scenarios of process intensification is very interesting. So I have a mostly a clarification question and then another question that I wanted to ask. So from the two scenarios of the extruder for trying to control the viscosity and producing the desired polyurethanes or polyethers, you show in that case that from ultrasounds and microwaves, at that case, you preferred the ultrasounds, while in the flow synthesis of the solids, the microwaves were the
The other
most...
way around. The other way around. With the reactive extruder, I showed you an example with microwaves, with the suspensions, the zeolite. I showed you examples of the microwaves.
Yeah.
Yeah. Go ahead.
Yeah, no, sorry. Yes, I just remembered you were showing the plots with the temperature, so it was indeed the microwaves. I'm sorry for this. So you did try the effect of both, and you just verified that in its case, it's one the controlling.
We did verify both, and it's not because I'm not showing the results that we made a clear decision on, yes, with reactive extruder it's only the microwaves, or with the COBR it's only the ultrasound. Definitely not. It was just out of time constraints that I had to decide what I was going to show. For example, we do see also very interesting results with ultrasounds, with the reactive extruders. But yeah, I mean, the thing is that you're working with these two distinct type of energy sources. I would always say microwaves, yes, good for heating, ultrasound more for mixing. Sometimes we see very strange results. In a particular case, we saw that the ultrasound was in some cases better than microwaves for the reactive extruder because of its heat formation. This is not completely clear to us at this moment whether that's a real effect. But it really depends on case by case, and I would not exclude at any moment any of these two technologies for the combinations with the reactive extruder and with the CLBR.
Okay.
Jorgos, if you want to add, please do.
No, I'm covered by the answer.
Perfect. And one more question about the flow synthesis of the solids. You did show some pictures about how of the particle size, the uniform particle size that you were getting. And indeed, particle size can be very important. Now you were doing it for zeolites, but for example, I guess if this extends in another application, like catalysis, you need to control one of the goals of flow synthesis to control the particle size. So my question is whether I know, for example, you can control the particle size depending on the flows that you do during the flow synthesis, but in your case, how would the ultrasound affect the particle size?
Ultrasound is known to a certain frequency ranges to provide cavitation. Cavitation is the formation of vacuum or gas-filled bubbles in a liquid which implode over time. They don't have a permanent lifetime, so they implode, and while imploding they provide very high shear forces, and these shear forces are basically used to impact solid particles and to reduce the size of particles or to clean surface solid surface areas. So this is a known effect. We've applied that both in batch and in COBRs to these suspensions. The original idea that we had is we know that with COBRs you can also keep your particles in suspension, and you can, depending on the oscillation intensity, you might be able to reduce the particle sizes as well. But the idea was that we would combine it with ultrasound to have on top of that some additional particle size reduction intensity, possibly also relaxing on the oscillation intensity. So that gives us a bit more, let's say, flexibility in terms of what is the required amplitude or the required frequency of the oscillation, that we can relax on that by adding the ultrasound. This is still something that we need to show or to prove that this is indeed the case, that you can relax on one intensity from one particular energy form, let's say, by adding another energy form. But this is at least the underlying idea. But both of them provide shear forces, and depending on the rigidity of the particles, these allow to reduce the particle size or not.
Okay, thank you very much.
I see we have a question from the audience that is a bit in common between the two presentations of Professor Stefanidis and Professor Van Garven, and is about, which transport phenomena, heat, mass, momentum, or reaction kinetic most often limit success process intensification in real industrial systems?
Yeah. Well, it's a nice question. It has to be understood that these phenomena are associated with timescales. And these timescales are competing because we're talking about serial processes. So mixing defines transfer of the molecules in the bulk. Then you have mass transfer that defines transfer of molecules from through an interface or over an interface. And then you have the reaction. And heat transfer and heat transfer timescale defines essentially the temperature at the point where the reaction takes place. So these are all competing timescales. It's not these limitations that or these phenomena that limit successful processification application. It's the other way around. Processification is here to address these limitations. That's one point. Then, given what I said before, that these time scales are competing, process intensification, most process intensification technologies primarily address transport phenomena. The idea is to alleviate heat and mass mixing, heat and mass transfer limitations in order to bring the system to the kinetically limited regime, and then you do what you can in order to speed up the reaction itself, in order to have a globally intensified process. So most of the PI technologies address transport phenomena. Which transport phenomena? That depends on the system under consideration. So for example, in polymer systems, mixing and mass transfer are the dominant limitations. Heat transfer also to a second extent. If we're talking about gas-solid systems, it's mainly energy or heat transfer limitations that dominate the system. In liquid phase systems, in general, it's mixing and mass transfer. Yeah? When you have a gas phase involved, and a solid phase that is less conductive, it's usually heat transfer that has to be, heat transfer limitation that has to be addressed. So it depends on the system, but primarily we address transport phenomena in order to bring the system to the kinetically limited regime. These phenomena are not limiting PI application. PI, again, is here to address these limitations. It's the other way around.
Thank you. I don't see any other questions from the audience, neither in the chat or in the Q&A.
Okay, so yes, if this is the case.
Yeah, if not, we can go to the closure of this coffee talk.
Yes, thank you very much, everyone, for joining today. I would also like to thank our speakers, Professor Stefanidis and Professor Tom Van Gerven, for members of the Working Party of Process Intensification, for being here with us today and giving us a thorough look on this discipline of chemical engineering. And we hope to see you all in our next coffee talk in the next months. Thank you very much.
Thank you.
Thank you, everyone.